Okay, it's pleasure to welcome you today the number Theory-4 online video. And I hope that by the end of the video you will have a better understanding of how should our approach be. Let's get started. And today I'm planning to divide my lesson into 4 parts, such as the Euclidean algorithm, linear Diophantine equations, Wilson's theorem, and the Chinese remainder theorem. So now we can start with the Euclidean algorithm. Okay, the first is the Euclidean algorithm. Okay. In this section, I describe a systematic method that determines the greatest common factor of two large integers. This method is called the Euclidean algorithm. For example, greatest common factor of 4147 and 10,672. What is greatest common factor? Notice that 1672 is equal to 4147 times 2 plus 2378. We use the steps in the Euclidean algorithm to write the greatest common factor of two integers as a linear combination of two integers. We will use the same step. I will take this and this. 4147 is equal to 2378 times 1 plus 1769. And again, we will take 2378 and 1769. 2378 is equal to 1769 times 1 plus 609. We are gonna take these two numbers, 1769, which means 609 times 1 plus 551. 609 is equal to 551 times 1 plus 58. So 551 is equal to 58 times 9 plus 29. On the final part, 58 is equal to 29 times 2. By the way, we can say greatest common factor of 4147 and 10,672 is equal to 2. We will take here the less quotient. The less quotient is 2. Okay. Are you aware of that or not? But we have two large numbers. For the small numbers, it's not difficult to find greatest common factor. For the large number, as I told you, we have to use the steps in the Euclidean algorithm to write the greatest common factor two integers as a linear combination of two integers. Okay, I write it now. By the way, you are gonna enter the municipality competition. Are you ready for that? What do you say? How is my voice? And what about my quality of the camera? Everything is alright? Is it okay? Okay. Synergy says yes. Thank you. Okay. Can I clean it? Let's continue with the second part, which means linear Diophantine equations. Okay. And the second part, we're gonna talk about linear Diophantine equations. So in this part, I'm going to show you equations in two variables called linear Diophantine equations. This kind of equations require integer solutions. The goal of this part is to present the set of points that determine the solution to this kind of equations. Geometrically speaking, the Diophantine equation represents the equation of a straight line. So here we can say as a 2.1, let me write it, a linear equation of the form ax plus by is equal to c, where a, b, and c are integers, where a, b, and c are integers, is known as a linear Diophantine equation. Let me give you another theorem also, 2.2. The equation ax plus by is equal to c has integer solution if and only if d divides c, where greatest common factor of a and b, if the equation has one solution, x is x0, y is y0, then there are infinitely many solutions. Infinitely many solutions. And the solutions are given by, this part is very important, focus on it, x0 plus b over d times t, and y is equal to y0 plus a over d times t. So which means t is element of integers. First write it, and after that we will solve a few questions to understand better. We have to practice. So we can say for ax plus by is equal to c, if greatest common factor of a and b is d, and d divides c, automatically we can say that there are infinitely many solutions on the equation for ax plus by is equal to c. But how can you find here the values? To find this, we will use for first x0 plus b over d, which means greatest common factor. B over d times t is the element of any integers. For y is y0 plus a over d times t as well. I have an example. Let me clean the first part. Prove that the equation, hi Zehra, the equation 4x plus 6y is equal to 8 has infinitely many solutions. Has infinitely many solutions. Okay. We will find here the pair of x and y. So for x and y, we have to prove there are infinitely many solutions. Okay, find pair of x and y. And I'm going to show you the solution step by step. Can I clean 2.2 if you don't mind? Okay. Blaže, welcome to the lesson, by the way. Okay. It's very nice to see you here. Okay. So the first, we have to find greatest common factor of 4 and 6. Greatest common factor of 4 and 6. What is it? It's 2. And 2 divides 8. 8 is divisible by greatest common factor of 4 and 6, which means 2. So we say there are infinitely many solutions, but we have to prove that. We use the Euclidean algorithm to determine m and n. First, here, determine m and n as 4n plus 6n is equal to 2. Can you tell me the possible values for m and n? What are our possible values for both m and n? Tell me the values just. 4m plus 6n is equal to 2 equation given, and we have to find here the value of m and n. Tell me the answer. M and N can be any integers, positive, negative, or neither. Thank you very much, Seneja. M is -1, N is 1. Yes, and after that, for the second, we are gonna make x0 and y0. To get x0, we'll multiply 4 by a -1. We have to find for m. For y0, we have to use here is 4 and n, 4n. So for m is -1, we got it. 4 times -1, which means -4. For y0 is 4 times 1, which means 4. And we got here x0 and y0. And after that, to find x and y, x is equal to x0, remember, plus b over d times t. x0 is a -4 plus b is 6 and d is greatest common factor 2. b is 6 and d is 2. 6 over 2 times t, which means -4 plus 3t. For y is y0 plus a over d times t, which means 4 minus a over d. And what is a? 4. d is 2. 4 over 2 times t is 4 minus 2t. Okay. So there are infinitely solutions. For x is -4 plus 3t and for y is 4 minus 2t. t is elemental integers. For example, for t is, let's take 1. So what is the value of x? 3 times 1, 3. -4 is -1. Y is 4 minus 2 times 1 is 2. 4 minus 2 is 2. For x is -1, for y is 2. We have to check it. The values provide the equation or not. 4 times a -1 plus 6 times 2 is equal to 8. So 4 minus 4 plus 12 is equal to 8. Okay, glad to have it. And the next theorem is called Wilson's theorem. Okay. Wilson's theorem says if P is a prime number, then P minus 1 factorial plus 1 is congruent. Let me write here. We don't have enough space. P minus 1 factorial plus 1 is congruent 0 in mod P. Okay. By the way, can I clean this solution? Okay. Wilson's theorem here, if P is a prime number, then P minus 1 factorial plus 1 is congruent in mod P. First, remember the factorial. And what is 5 factorial? We will take the product of all numbers from 5 to 1. 5 times, 4 times, 3 times, 2 times 1. Which means 120. Okay. So for P we can take 5 just to show it. 5 is a prime number. So 5 minus 1 factorial plus 1 in mod 5. What is it? 5 minus 1 is 4. 4 factorial plus 1 is congruent in mod 5. We have to find it. 4 factorial is 24. 24 plus 1, 25. When we divide 25 by 5, what is a remainder? 0, yeah. Okay. So if P is a prime, thus P minus 1 factorial plus 1 is congruent 0 in mod P. We can prove for P is 7 and for other primes. Okay. Did you get the point here? Before start the next theorem, by the way, remember Fermat's little theorem and Fermat theorem. If P is a prime and P is not divisible by A, in this case, according to Fermat's little theorem, A to the power of P minus 1 is congruent 1 in mod P. Means when we divide A to the power of P minus 1 by P, we will get 1 as a remainder. And the next Fermat theorem a to the power of p is congruent a in mod p. Okay, let me clean it. Okay, the fourth one, the Chinese remainder theorem. The Chinese remainder theorem, made in China. So in this section, I'm going to give you the solution of a system of congruous having different module. For example, find a number that leaves a remainder of 1 when divided by 2, a remainder of 2 when divided by 3, and a remainder of 3 when divided by 5. As a division algorithm, when we divide a by 2, remainder is 1. By 3, remainder is 2. By 5, remainder is 3. What is the value of a? What is a? So if we'll convert the division algorithm to modular arithmetic system, a is congruent 1 in mod 2, a is congruent 2 in mod 3, and a is congruent 3 in mod 5. We have to find the value of a, but there are many steps actually, so let me show you the steps. A is equal to, a is congruent a1 in mod b1, a is congruent a2 in mod b2, a is congruent a3 in mod b3. And after that, first we have to find least common multiple of b1, b2, and b3. Least common multiple b1, b2, and b3. Let's say least common multiple of b1, b2, and b3 is n. For the second step, we have to find k1, k2, and k3. N over b1 will give us k1, n over b2 is k2, and when we divide n by b3, the answer is k3. And after that, for the third step, we have to find c1 d1, c2 d2, and c3 d3. To find this, k1 times c1 is congruent 1 in mod b1, k2 times c2 is congruent 1 in mod b2, and k3 times c3 is congruent 1 in mod b3. And from here, from the first, we have to find c1 is congruent d1 in mod b1. From the second, c2 is congruent d2 in mod b2, and from the last, c3 is congruent d3 in mod b3. For the final step, a is congruent k1 times d1 times a1 plus k2 times d2 times a2 plus K3 times D3 times A3 is congruent A in mod N. In mod N. Okay, first write all steps, and after that we will start to solve this problem, okay? You don't have a worry. It seems complicated, but we will make it easier, no problem. Of course, it's very useful. You'll understand what I mean to say. Okay. Can you start to solve the problem? We are perfect together, stick together, so let's solve the problem together, okay? Give me your hand. Let's start it. First we have to find least common multiple of 2, 3, and 5. First, least common multiple 2, 3, and 5, which means 30. And after that, for the second step, we will find K1, K2, and K3. K1 is n over B1, right? 30 over 2, 30 over 2, which means 15. K2 is 30 over B3, which means 3 is 10. So K3 will be 30 over 5 is 6. Okay. We found K1, K2, and K3. For the next step, we write K1 times C1 is congruent 1 in mod B1. You can compare it. K1 times C1, 15 times C1 is congruent 1 in mod 2. 10 times C2, 1 in mod 3, and K3 times C3, which means 6 times C3 is congruent 1 in mod 5. Okay. And after that, here we have to find D1, D2, and D3. When we divide 15 by 2, what is remainder? Tell me the remainder. 15 by 2. Yes, it's 1. So 1 times C1 is C1. C1 is congruent 1. 1 is D1 in mod 2. C2 is congruent. 10 is divided by 3. Remainder 1 as well. So 1 times C2 is C2. C2 is congruent 1. It's D2 in mod 3. 6 by 5 remainder is 1. 1 times C3 is itself. C3 is congruent 1, which means D3 in mod 5. Okay. We found everything here. So for the last step, K1, D1, and A1. K1 times D1 times A1 plus K2 times D2 times A2 plus K3 times D3 times A3 is congruent A in mod n. And what is n? N is 30. Okay. K1 is 15. D1 is 1. A1 is A1, A2, and A3. A1 is 1 plus K3 is 10. D2 is 1 and A2 is 2 plus K3 is 6. D3 is 1 and A3 is 3. Is congruent A in mod 30. Okay, 15 times 1 times 1 is 15 plus 20 plus 18 is congruent A in mod 30. 15 plus 20 is 35 plus 18 is 53 is congruent in mod 30, which means 23, right? When we divide 23 by 30, the answer is 23. Okay, we got the solution. 23 for A is 23. 23 plus 30, 53. 53 plus 30, 83. 83 plus 13, 113, and so on. We can take all those values for A. Check it. 23. 23 divided by 2. Remainder is 1. 23 divided by 3. Remainder is 2. 23 divided by 5. Remainder is 3. Look at the 453. 53 is divided by 2. We will get 1 as leftover. 53 is divided by 3, left over is 2. And 53 is divided by 5, 3 is a leftover. Okay, so we got the solutions here. Understand? Of course, you have to practice a lot in this part, and after that, you will have a better understanding. And I hope this guides you in solving problems. And I'm planning to record number theory 5 video as soon as possible before municipality competition. So keep in touch. Let's stick together, okay? And after that, take a look at the next video when I will explain. Okay, that's enough for today. 42 minutes passed almost. Thank you very much. Good luck. Bye bye.